Good evening, everyone. I'm Kashif Rabbani. Today I'm going to present our work Sparkle Query Optimization using shape statistics. Knowledge graph depict knowledge in terms of entities and their relationships in the form of nodes and edges as shown in this example knowledge graph. They're being used at enterprise level by many organizations such as Google, Amazon, Facebook, etc. etc. With this extent, a lot of open knowledge graphs are also being produced such as DBpedia, Wikidata, and Yago. Since they are very used, now we move from the need of simple to complex Sparkle queries, such as an example complex Sparkle queries on Wikidata is shown here. In order to represent knowledge graphs, RDF is a standardized data model. It consists of a set of triple patterns. For example, given Peter and Kim, where Peter is a student and Kim is a professor. Peter is advised by Kim. Here, Peter is subject, advisor is predicate, and Kim is object. Together, they form an RDF triple. And collectively, an RDF graph is a set of various RDF triples. To query this RDF graph, Sparkle is a standardized query language. It consists of a set of RDF triple patterns, which are also known as basic graph patterns. For example, in this query, we have various Sparkle query patterns, Sparkle query triple patterns. To answer these basic graph patterns, we require a mapping between the variables of these triple patterns to the values in the RDF graph. Complex Sparkle queries consist of many triple patterns, hence a lot of joins. And the query execution time is impacted by the join ordering of a given query. For example, given this example Sparkle query, one way to execute this is using join ordering A, which takes around 10 seconds to execute. If we swap this join ordering by moving these two triple patterns, it's going to take half the time as compared to B. And if we further swap this join ordering to join ordering C, it's going to take 2 times less time as compared to A. This is due to the difference in the number of intermediate results. We process small number of intermediate results in B as compared to A and in C as compared to both A and B. Now the question is, how can we compute efficient join ordering? So cardinality estimation comes into account to compute efficient join ordering. For example, joining triple patterns by estimating their cardinalities. For example, for these triple patterns, these are the estimated cardinalities. How can we compute efficient cardinality estimates? How can we collect statistics of the RDF graph? And how we can compute efficient join ordering using these estimates. So we need the structural information of the RDF graph to compute these estimates. For this purpose, we exploit a state-of-the-art RDF validation language called Shackle. It was originally designed for validation. It became W3C recommendation in 2017 and consists of nodes and property shapes. Our intuition is to exploit Shackle's structural information with statistics. For example, for the given Shackle shapes network, we can annotate it with the different statistics such as count, distinct count, min, max count for the nodes and shape properties and utilize them for the purpose of query optimization. So our approach in a nutshell is that given a knowledge graph and Shackle shapes graph, we have an annotator which is gonna annotate the Shackle shapes with the statistics of the RDF graph, and we name them as shape statistics. Once the shape statistics are prepared, with the node shapes having all the min, max, distinct count, during optimization, while query planning, we use these shape statistics to compute cardinality estimates. Now, let's take an example of Shackle graph. So given our example RDF graph for Peter and Kim, here we show the Shackle shapes for student and professor, where each shape represents various constraints and shape properties. We exploit this structural information and extend it with the statistics of the RDF graph. For node shape, we collect distinct count, and for each property shape, the count, distinct count, and min-max count of these properties. So we name these as shape statistics. So given these shape statistics and a Sparkle query, we propose a set of formulas to estimate the cardinalities of individual triple patterns of the given query. So given these formulas, we have a triple pattern cardinality estimator where we provide its all the inputs, and for each triple pattern we compute the estimated triple pattern cardinality using the shape statistics and these formulas. Once we have the estimated cardinalities for each individual triple pattern of a query, we propose a set of formulas as shown here in formula 1, 2, and 3 to estimate the joint cardinality for various joins such as subject-subject, subject-object, and object-object among triple patterns. These formulas are actually inspired from relational databases. So we computed the estimated triple pattern cardinality in the last slide. Now we take the information distinct subject and distinct object count for each triple pattern from shape statistics, and then we make use of these formulas to compute the joint cardinality. For example, to compute the estimated joint cardinality for triple pattern 1 and 2, where there is a join between subject of triple pattern 1 and subject of triple pattern 2, we use the formula number 1, and here is the estimated joint cardinality. Similarly, we move further and we compute the estimated joint cardinality for triple 2 and 3, where still there is a join between subject-subject. Then we move further and we compute joint cardinality between triple pattern 3 and 4, where the join between subject and object, and so on. So now as we know how to exploit shape statistics to compute the cardinality estimates, we propose a join ordering algorithm to make use of these estimates and propose efficient join ordering. So this algorithm actually iterates over all the triple patterns, estimate the joint cardinalities of individual triple patterns, and then it combines with all the other triple patterns to estimate the joint cardinalities using our formulas and computes the cost of each plan. And finally, it computes the efficient join ordering based on the least possible estimated cardinality. We experimented on a large machine with large synthetic and real data sets with a specified number of queries, having query evaluation matrix as the query runtime, the queue error, and the cost of the query. All the methods that we tried take around 20 milliseconds as a planning time, which is negligible as compared with the overall query runtime for all the approaches and the queries. And we set the query timeout as 10 minutes for all the queries that we execute. We have implemented our approach using shape statistics in Apache Jena, where we compare it against the global statistics collected over the whole RDF graph, Jena R, query engine, GraphDB, characteristic sets, and graph summarization approach. The pre-processing time required to generate shape statistics is 2 to 4 times less as compared to some RDF and characteristic sets approach, and it is 2 orders of magnitude less in terms of space as compared to these approaches, as shown by this chart. For the query runtime analysis, we see that the shape statistics are effective in type-defined queries, and the Jena has poor performance overall due to heuristics-based query engine. The SumRDF approach is competitive to all other approaches, and shape statistics approach outperform other approaches, mostly in complex queries. Also, we noticed that as compared to the theoretical best optimal query plan, which could be produced by a best system, our approach is only slower overall from 14 to 30%. So for these specified queries, our approach outperforms the rest of the approaches on Lubim dataset, and on Yago 4, we are outperforming the other approaches mostly on complex, some of the snowflake, and star queries. We also show Q error analysis, which quantifies the ratio between the actual and estimated final cardinality for the given Sparkle query. On Lubim, some RDF approach has low value of Q error. However, for the real dataset, that is Yago, our approach has a low value of Q error overall. Okay. So in summary, our approach supports efficient execution of complex queries with less pre-processing overhead, space efficient, and overall outperforming in 75% of cases of type-defined queries. In future, we are going to integrate it with some Sparkle query engine. All the resources are available on our website, and I'm happy to answer any question. Thank you.